Okay, so now I'm going to explain this other problem called the minimum cost network flow problem. And this is actually a generalization of the transportation and the transshipment problem. Um, I will start by reading the prompt and then I will explain what are the differences and the similarities and how we're gonna tackle these differences, okay? So consider a set of M locations. Okay, now we make no distinction. Locations are all in the same set. If you remember on the transshipment and the transportation problem, we always differentiate like different sets where like some of the locations are suppliers, some are customers, some are transshipment points, and they're all in different sets. In this case, we just have 1 through M locations, okay? And of course, each of them represents a supplier, a customer, or a transshipment point, but they're all in the same bag, if you will. Now, if we have the information about the supply at each location and the demand at each client, and we also know the cost of shipping a unit of product between any two of those locations, how can we find the optimal plan of action, right? The one that minimizes cost, but that satisfies all the constraints, right? So let's just begin by making a diagraph. That's what we always do, right? And then I'll explain the difference between. Yes, and then I will explain the difference between this setup and the setup on the transshipment problem, right? Here, if you were doing the transshipment problem, maybe I'll just draw it here. You would have like a set of suppliers on one side, right? Then you would have a set of transshipment points, and then on the other side you'd have a set of clients, right? And then you would have arches going between this set and this set, between this set and this set. And it would look something like this. You'd have over here a bunch of arches, another bunch of arches going this way, right? And so on. But of course, this is not completely realistic, okay? Because if these are the warehouses, and these are the transshipment points, and these are the clients, right? Who is to say that I'm not allowed to send stuff from the warehouses to the clients directly without going through the transshipment point? So the transshipment problem, this is the, I'll just call it the transshipment problem. The transshipment problem, it's a little simplified. It makes some assumptions. Specifically, it makes the assumption that everything going from the warehouses to the clients has to pass through the transshipment points, right? What we're going to do now is generalize completely that approach. And you'll see that it actually makes the formulation easier, right? So let's just draw a different diagram, right? And this is the actual big picture, right? For the minimum cost network flow problem, okay? Now the situation is different. Instead of locating all the supplies and all the demands, what we're gonna do is actually spread everything out. We're gonna have what seems like a more messy diagram. We have transshipment points, clients, and suppliers all mixed up in the same area. They're all part of the same set. But now, instead of defining very restricted arches, we're going to start by making an arch between any 2 points, right? You could have this way, that way, the other way, right? Then you could have one going this way, and so on. And they're all connected in some way. And even though I'm only drawing in arrows in one direction, this would be maybe a complete diagram, so you'd have arrows going in all directions, right? Because in reality, when you have factories and you have retailers, there's nothing forbidding you from sending product from one of your warehouses to any of the final retailers. Okay, so let's just assume. I know it looks messy. Now let's make the distinction now between the points, right? We said that some of them are warehouses and some of them are transshipment points. How can we model that, right? What we do is the following. We defined these parameters. And these are going to be net supplies, right? We can call them like this, BI. And these are going to be defined for all I, for all I and up to M locations, right? So we're gonna have B1, B2, up to BM. The important thing here is to explain that BI, it's going to be positive if location I is a supplier, right? It's going to be 0 if location I is a transshipment point. And it's going to be negative if the location I is not a supplier and it's not a transshipment point, if it's a client, right? So in a way, we're using a single parameter to represent supply and demands all together. Make sense? Right? So essentially, yes, you could think of it as a, let's see, it could be BI, it's going to be equal to the supply, but BI would be equal to the negative demand, right? If the demand, if you had the demand, if the demand at a client was 30, then the net supply would be negative 30, right? I think that's clear. Okay. And then the other parameters you would have would be the costs between arches. But we can easily define those like we've been doing up to now, right? It would be cost defines, so that parameter ij is just the cost of shipping one unit from location I to j. And notice that in here, we're not going to make any distinction. We're allowed, I mean, we're allowed to send product from a producer to another producer, right? There's nothing, if this location is a warehouse and this location is a warehouse, I'm perfectly allowed to send stuff from here to here, right? If this is 1, 2, 3, I'm gonna define ij for all ij. Actually, yeah, I think we're gonna define for all ij such that I is different from j, right? That's the only restriction. We are not going to send stuff from one place to itself, though. We're not gonna allow loops in the graph, but everything else is allowed. Any other 2 points can be connected, and we just need to make sure for I different from j and ij, both of them in the set of M, right? Okay, I think that's mathematically correct. So we have costs, and we have net supplies. Then with all these parameters, we can go ahead and get started with the objective function, for example. Actually, no, for the decision variables, right? And this is no different from what we did in the transshipment problem or the transportation problem, the only way to describe the whole course of action is to basically specify how much you're sending along each arch. And I mean, since we already have a parameter, we already used a very similar approach here. When we defined the parameter, we had to define it for every possible arch. So now when we define the decision variable, we also have to define it for every possible arch, and the index set, it's going to be the same. So we can call it xij, right? And that's going to represent number of units sent from I to j, and I and j satisfy all those same conditions we specified earlier, right? Which are really no conditions. The only condition is that you are not going to be sending stuff in circles. That's the only thing, right? We have those decision variables. We don't need to worry about anything else. Now we have to write the objective function. And in this case, it is exactly the same as in the transportation problem, right? When they give you a course of action, how can you calculate its cost? It's going to be the number of units you send along each arch multiplied times the cost per unit sent along each arch. So it'd be xij times cij for all possible pairs, right? And then how would you do that? I think we can just write it this way. There are better ways to write it, but let's just do this way. So for I from 1 up to m, and then for j, right, we can just say from a belonging to that same set, but specifying that j is different from I. I think that makes sense. Okay, that would be the objective function, and then of course you have to specify the direction, and in this case it's a minimization, because what we want to do is minimize the total cost, right? Then all we have left is the constraints, because we need to make sure, I always say the same thing, if you have this objective function and you feed it into the optimizer, simplex is directly going to give you a 0, right? Or even negative numbers, because if you don't specify that you must meet demand, yeah, no one will do it for you. You have to do it, okay? So you have to do constraints, and let's just try to remember which constraints we need to do in this case. Clearly, now so this is the thing, now we don't have the same sets that we had on the transshipment problem. In the transshipment problem, we had these clear definitions, like these are the warehouses, and we must meet supply constraints for the warehouses. Here we have the clients, and we must meet demand constraints for the clients. Now on the minimum cost network flow problem, we don't have that same organized view. Now what we have is a bunch of net supplies, right? But you'll see that you can actually specify supply and demand constraints all in the same statement. Okay. So let's think about this. Let's say, I don't want to spend too much time on this, but picture this point, right? And suppose that let's say this is point 1, so B1 equals 30, right? So since the net supply is positive, we know that it's a supplier, remember? Okay. And we have several arches going into this supplier. We also have several arches going out, right? If we know something for sure, is that however much comes in, right, at least exactly 30 units more are going to come out, right? If nothing goes in, 30 go out, because that's the supply provided by that location. it's like a source, right? If you had a faucet and you have a flow of liquid coming in, and you also have a flow provided like by the source, you know that that's going to be added to the total number coming out, right? So it's the net flow that this location is going to add. If on the other hand you had a another location where the right, so we have x coming in, and this would be x plus 30 no matter what, right? If on the other hand you had a location that it's actually a consumer, a client, right? Because the demand is negative. The net supply is negative, the demand is positive. What you would infer is that everything going in, right, it's going to be 20 units more than what's coming out, right? And if the location was a transshipment point, that means that nothing can get stuck on it, and everything coming in, it's going to be equal, exactly equal to everything coming out, right? And that would be the same approach we used here. So now remember what we did for the transshipment problem. We said like everything coming out is going to be exactly equal to everything coming in, right? In this case, we're going to rearrange that equation a little bit. Let's say everything that goes in, actually I'll do everything that goes out first, and you'll see why. Everything that goes out is everything goes out from node, we can say node K, from node K, goes out from node K. It would be the sum of all the variables. These variables are xik, right, for all I in this set of nodes, and of course except K, right? If you add everything going into K, and then you subtract everything that's going out, it would be xkj, and again it would be for j and m, but j different from k. You would expect that, right? Everything that goes out, this is everything that goes out, and then everything that goes. Did I do it wrong? Oh, I flipped it. Hold on. Goes out from node K, and I said everything that goes in. Let's just switch the sign. Oh, sorry about that. So you have everything that goes into node K is here, goes in, right? And then we have everything that goes out. So I'm going to add everything that goes out and subtract everything that goes in. I don't know, was that too confusing? The upshot here is basically if point K, if node K is a supplier, I know that whatever goes out must be like 30 units over what goes in, right? So that means that BK is going to tell me exactly, how much the difference is between what goes in, what goes out and what goes in. Yeah. And this, of course, is going to be defined for all possible K in the set M, right? 1, 2, 3, up to M for all of them. Yes, the other constraint, this would be the first set of constraints. The other set of constraints is the same as always, xij, it's greater than or equal to 0, right? Because you don't want to be sending negative units. Yes, and I think that's a minimum cost network flow problem. Sorry about this confusion. Yes, hopefully that's clear.